Okay, so that's what's going on here is we are multiplying each time by that value b, which means that Jerry's equation is $5,000 starting value, y-intercept, multiplier 1.0175 raised to the x power. But again, x is the number of quarters. So 10 years. How many quarters is that? In other words, I can't put a 10 here because that would be 10 quarters. 10 quarters is, less than 3 years. It's like 2.5 years. So what number should I put here to represent 10 years? How many quarters in 10 years, guys? 40. So for 10 years, I got to put in a 40. So in other words, his entire calculation needs to be done in quarters because that's how often his money is being compounded. So the bank is giving him interest every quarter. Yeah, I hate it when it does that while I'm writing. And there we go. So 5,000 times 1.0175 raised to the 40th power. And easiest on a calculator, just literally type it in the way that you write it on paper, with the parentheses and everything. That way you don't have to worry about, well, what do I do first? Do I multiply? Do I do the exponent? Exponent does come first, by the way. So if you were going to do this step by step, you would have to do the exponent first and then multiply. But if you just type it all in like this, the calculator knows the order of operations. The calculator is programmed to do exponents before multiplication. And we end up with $10,007.99. So just over $10,000. So it looks like John made the better investment for 10 years. Okay. Now, that might be surprising because I had mentioned before that compound interest is better than simple interest. But, this is 12% versus 7%. So this is a significantly better interest rate, 5% better. But look at what happens if they were to keep these accounts open for 20 years. So let's say what happens to John in 20 years. 600 times 20 plus 5,000. Okay, so in 20 years, he's going to get $12,000 here plus 5,000 is 17,000. So in 20 years, he now has 17,000. Jerry, if we do 20 years would be 80 quarters. So 5,000, 1.0175 raised to the 80th power is, I didn't write it all out, but that's what I did is plugged it into my calculator, is $20,031.96. So it looks like in 20 years, the compound interest ended up doing better than the simple interest. And if we kept going, the compound interest would stay the better investment. So is compound interest better? Yes, in the long run. If you're only going to keep your money in the account for a few number of years, this one actually is better because the interest rate is so much higher. But once you hit that threshold, and I think it comes out to about 13, 14 years where they actually end up meeting, this one does better. So it's all about how long you're going to keep your money in there. But in the long run, the compound interest, the exponential, is going to end up being better. And to illustrate that, I have an example to look at. And let's see. Every time I do that, it just goes all over the place. That's what I want. And then I want my Zoom people to be able to see this. So I'm going to share. Come on. I'm going to share my screen. And we're going to minimize all of the Zoom windows. Okay, so if you take a look at the screen, I'm going to give you two possible scenarios. Let's say you go out to get a summer job and you have two options. Employer number one says, great, I'm going to hire you for the summer. On day one, I'm going to give you $100. On day two, I will give you $200. On day three, I will give you $300. On day four, I will give you $400. And we will continue that throughout the summer. Obviously, this is a great deal. I don't think you will find anyone who will pay you $100 to start and then increase it by $100 every day. But, you know, idealistic in a wonderful world, you might be able to find someone to do that for you. So by day four, you are earning $400 for the day. Employer number two says, well, I will start you off with 1 penny, but then day two, I will give you 2 pennies. Day three, I will give you 4 pennies. Day four, I will give you 8 pennies. So in other words, I am going to double your salary every day, starting with 1 penny. So if you were going to get one of these jobs for the summer, which one is better? Okay, Danny says the second. What do you guys think? It does double, but let's take a look. Day four, job one is way better because I'd rather have $400 than 8 cents. If we take a look at the graph here, this is job one, the linear. So you can see job one is growing linearly. Job two is exponential because it is doubling. You can see in the equation, the 2 right here. So if I turn that one on, we can see job two, but look, it's so flat. But remember, exponentials start off very flat, and then it starts to increase over here. So let's take a look at what happens at day 10. Day 10 is 2 weeks into your job. I'm assuming, 5 days a week. So 2 weeks into your job. Option one, you can earn $1,000 for your day, or job two, you earn $5.12. So obviously $1,000 is better than $5.12. But if we keep going 1 week later, so 15 days of work, we got $1,500 here, but notice this one is starting to catch up, $163.84. Another week, day 20, I have $2,000 here. Option two, I have $5,242. In fact, if I add all of these amounts from job one, they only add up to $4,000. They're actually not as good as, the salary on day 20 at the second job. If I keep going, day 25, this is 5 weeks into your job. Job one is going to give you $2,500 for the day. I mean, that's a great salary. I mean, I'm not going to scoff at $2,500 for a day's work. I mean, that's an awesome salary. But take a look at option number two. You are now earning $167,772 for the day. And then that's just going to keep increasing. Day 26, the next day, 2,600 versus $335,000. Day 27, you're now earning $671,000 a day. If I keep going, it gets, ridiculously high. This is basically $1.3 million. So by day 28, you are earning over $1 million a day. And if you take a look at the graph, and you can see why this happens, look at that exponential. Once it starts to shoot up, it shoots up super, super fast. When you are doubling something, you are increasing incredibly fast, even if you only start off with 1 penny. Okay, so the moral of the story is go home and ask your parents for a new allowance system. Say, hey, why don't you give me 1 cent for my first day of allowance? You can even say for the first week, my first week of allowance, I want 1 penny. Second week of allowance, I want 2 pennies. and then 4, and then 8. By week 28, if we're counting by weeks, that's less than a year. So by less than a year, your parents will then be paying you $1.3 million in allowance. If you can convince them that this is a good plan. They might not think about it too much, and they might think it is a good plan at the beginning until the growth starts, and then they realize, yeah, we cannot do this. Okay, but right around, it's going to start getting ridiculous in here as far as allowance goes. They're not going to probably give you hundreds of dollars of allowance each week, but somewhere between week 10 and week 15, it's going to start exploding. Okay, so bottom line is exponential growth will always catch up to and beat linear growth massively, just like this, every single time. There might take a while, like we saw John and Jerry, and it took, over 10 years for the exponential growth, the compound interest to do better, but it always will, always. So even though this one grows very slowly at the beginning, there will come a point where, boom, it shoots up and becomes so much better than linear growth, okay? So exponential growth always overtakes linear growth. Okay, so we are going to look at specifically some more exponential and linear growth today. Specifically on your notes, we are going to look at pages 6 and 7, which I think I was in the process of inserting them into my notebook, and then I got distracted and I did not insert them into my notebook. So I'm going to do that really quickly while you guys, yep, see, I'm right here on the page I was going to do it on, while you guys open it up on Schoology. It is on Schoology. It's just not in my notebook yet. And hopefully, yeah, an error message, so I got to reopen it. Okay, so my pages are inserting, which means they should show up right there, and there they are. Okay, so we're going to do more of really what we've done before. So we're just looking at a couple of more examples of growth and decay. This is exactly the same thing we looked at when we were doing geometric sequences. So it really is the exact same thing with the percent multipliers. So when a quantity increases or decreases by a certain percent, so whenever you are told something is going to increase by a certain percent, you know that that growth is going to be exponential. Sometimes it'll even say, this thing is going to grow exponentially. Then you obviously know it's exponential. But whenever there's a percentage involved, it's going to increase exponentially, okay? So how do we figure out how it increases? Well, for growth, your B value, your multiplier, is 1 plus your percentage. If you are decreasing, fancy word for decreasing is decay. Decay means to decrease or shrink. You do 1 minus your percentage. All percent values need to be converted to a decimal first. So remember that to do that, you take your percent value and you divide by 100. That's how you convert a percent to a decimal. That's the same thing as move the decimal 2 places to the left. So if you don't want to hit the divided by 100 in your calculator, in your mind, you can just move the decimal 2 places to the left. Okay? So Jackson just purchased a new car for $35,000. If the car depreciates, fancy word, that means loses value. So the value of the car is decreasing at a rate of 8% each year. So we're decreasing by a percentage. So this is going to be exponential decay. Decay is the opposite of growing. So it's going to be decreasing exponentially at a rate of 8% per year. So the first thing we need to do is know that 8% is 0.08. So we need to be able to take our percentage, convert it to a decimal, and then we can calculate B. When something is decreasing decay, we do 1 minus the percent, and the percent needs to be written as a decimal. So we're going to do 1 minus 0.08, which is going to give me 0.92. So he is losing 8% of the value of his car, but he's keeping 92%. That's really what that multiplier is representing. He loses 8%, but he's keeping 92%. So every year, his car is going to be worth 92% of what it was worth the previous year. And that is the same thing as saying you're losing or decreasing by 8%. Table is not needed here, but if you wanted to do a table, we'd have X and Y, and this would be years, and this would be the value of the car. When he drives it off the lot, it's worth $35,000. 1 year later, we multiply by 0.92. And his car is now worth $32,200. Okay, and how I figured that out is right here. I multiplied by 0.92. So just multiply by 0.92 and you can figure out the value for the next year and the next year and the next year and the next year. Of course, you don't want to do that 10 times in the table. It's better to write an equation. Okay. Y-intercept initial value is $35,000. The multiplier is 0.92. And X is the number of years. So his car is going to depreciate 10 times in the next 10 years. So to figure out the value of his car after 10 years, we do 0.92 to the 10th power. So 35,000 times 0.92, raise that to the 10th power, is $15,203.60. Now, when you're doing delta math, you need to read the problem because they probably asked you to round a certain way. They might say round this to the nearest hundreds. So then you go to the hundreds, which is the 200 right there, and you say, well, is that closer to 200 or 300? It's closer to 200. So you would round to 15,200, okay? Which would also make sense for the car because like if you were gonna put your car like on Craigslist to sell it, you probably would not put that price because that looks kind of funny. So most people would sell their car for, hey, I'll sell it for $15,200. Or maybe if you want to sell it even quicker, you lower the price and maybe, you know, to the nearest thousands and just say 15,000. Okay? Technically, this is the accurate estimate all the way out to dollars and cents. Okay, next problem. Professor Pietro has just developed a new Super Bowl. You have been asked to test its rebound capabilities from your experiment. So you bounced his ball several times to figure out the rebound ratio. And you figured out, hey, if I drop it from 200 centimeters, the first bounce bounces up to 210 centimeters. So if I drop it from 250, so that would be no bounces. X is the number of bounces. If you drop it, it hasn't bounced yet from 250, one bounce later, it goes to 210. Okay? So X is the number of bounces and Y is the height. So we need to figure out the multiplier. We need to figure out what B is. We know that you multiply by B to get the next value in the table. It's also called the rebound ratio. When we were doing this with geometric sequences, we called it R because it's a common ratio. So it can be called multiple things, but B, the growth factor, the multiplier, the common ratio, rebound ratio, it's all the same thing. But what I do know is that 250 times B equals 210. To get from 250 on my table, I multiply it by B and then I get to 210. So B is going to be 210 divided by 250. So B is 210 divided by 250, which comes out to 0.84. Notice that value is less than 1. This also means the ball bounces 84% of the way back up. Or I could also say the ball height decreases by 16%. Okay. How did I know that? Well, because 1 minus 16% is another way of getting 0.84. Of course, I didn't know that at the beginning, but I know it now. So I now know that, hey, this ball is going to decrease its height every bounce by 16%, which is why the rebound ratio is 0.84. Okay, predict the height of the bounce if you drop the ball from 25 feet. So we're going to drop the ball from 25 feet, and we know that the next bounce is always 84%. So 25 times 0.84 is 21. Oh, could have figured that out, just not zeros there. 21 feet. Okay. So if you drop the ball from 25 feet, it will bounce back to 21 feet. C, write an equation for the bounce heights. Exponential is always A times B to the X. So this is going to be Y equals initial height is now 575. B is 0.84 because it's the same ball. And X is the number of bounces. So if you drop this ball from 575 centimeters, this is the equation that will calculate the height after any bounce. So if I want to know where is this ball going to be after 12 bounces, I'm going to put a 12 into this equation. So 575 times 0.84 to the 12. 575 times 0.84 raised to the 12th power is 70.96. And this would be centimeters because the 575 is centimeters. Okay, so if you took this ball, Dr. Pietro's ball, dropped it from 575 centimeters and let it bounce 12 times, that's how high it would still be bouncing at that point. So after the 12th bounce, it would reach a height of just about 71 centimeters. Okay. So, 2 more examples. 600 grams of a radioactive isotope decays. Decays means the opposite of growth. It means it decreases. So if something decays, it's shrinking, it's decreasing at a rate of 2.45% each day. 2.45% is 0.0245. That's what 2.45% is. We are decreasing. So we're going to do 1 minus the percent. So this substance decreases by 2.45% each day, which means it retains or keeps 97.55% its amount. So every day it keeps 97.55% of its amount because it's decreasing by 2.45% each day. So how much will be left after 100 days? Well, let's set up our equation. Starting value, 600. The rate of decay is 0.9755 raised to the x. X would be measured in days because this percentage is measured in days. So whatever the percent is tells you what x is going to represent. So since we're counting by days, this is going to be days. Good. So 100 days. Let's figure out what's going on 100 days in to this lab experiment here. The 0.9755 raised to the 100th power. And I get 50.22 grams. And again, on Delta Math, make sure you read where they want you to round to. They tell you. It says round to the nearest gram, that would just be 50. It said round to the nearest tenth, that would be 50.2. This is to the nearest 100th gram. Okay, so just read carefully, make sure you round correctly. Okay, our last example is population. The population of a certain town is growing. So this is growth. Growing means it's increasing by 5.6% each year. 5.6% is 0.056. That's what 5.6% is in decimal form. So since we are growing, we're going to do 1 plus 0.056. That's going to be 1.056. Okay, so when you grow, you do 1 plus your percent. Percent needs to be written as a decimal. When you are decreasing or decaying, you do 1 minus. If you're doing compound interest, you do 1 plus, but then you got to change this based off of your number of periods. In other words, if that's your annual interest and you're compounding quarterly, you got to divide that by 4. If you're compounding weekly, you divide that by 52. So however many, whatever it is, fit into 1 year. Daily, 365 days, you divide by 365. Okay, so the population in 2020, the population is 40,000. What do we expect the population to be in 2035? Now, X and Y. I could put 2020 here, but I would much rather start with 0. And I can say, you know what, year 0 is going to be 2020. So the year 2020, well, I'm going to call that year 0. I can start year 0 wherever I want. So this is exponential growth. In order to answer the question, I just have to start the growth at some place in time. So why not start it at 2020? It's the smaller of the two values right here. So in 2020, the population was 40,000. So X is going to be the number of years since 2020. Oops, 2020. And then this is the population here. So 0 is 0 years since 2020. That's 2020. So what we want to do is figure out what's going on down here in year 2035. How many years has it been? From year 2020 to 2035, how many years are we talking about? 15. So we're really trying to figure out the population in 15 years from now. So they just asked it differently. Instead of saying, hey, today the population is 40,000, what's going to be the population in 15 years from now? It's the same thing as saying in 2020, this is the population, and what's the population going to be in 2035? So in other words, you got to figure out, oh, well, they're just talking about in 15 years. So my equation is going to be my starting value in year 0 times 1.056 raised to the x power. So that's my general equation. X is the number of years since 2020. So 2035 is 15 years since 2020 has passed. So in year 2035, which is a total of 15 years from now, we're going to plug in a 15. 15 years from now, you guys will be like pushing 30. Some of you might be married, have kids, have careers. But believe it or not, 15 years goes by really quickly. Okay. This is what I got on my calculator, 90,577.17. But since this is population, I'm just going to round to the nearest whole number because you can't have 0.7 people. So my population is measured in people. So I estimate that in the year 2035, this town would have 90,577 people. Of course, this is just an estimate. It says, what do we expect? Because this is just a model. We cannot predict the future. We do not know for certainty that this town is going to grow by exactly 5.6% every single year for the next 15 years. We're just using this as a model based on what we have seen happening. So we've seen that this town has been growing, and we predict that it's going to continue to grow at 5.6% each year. Based off of that, this is our estimate. Okay, so it is just a model. Statisticians like to say that no model is perfect, but many models can be useful. So even though that might not be a perfect prediction, it still might be useful information. So the town could say, hey, in 15 years, we're going to more than double in size. We should probably be preparing for that, with building a different number of homes and stores and commercial areas and all of that. Okay, so that's the notes for today. And if you go on Delta Math, that's what you're going to be doing, is doing word problems that either deal with a increase or a decrease, a growth or a decay. And those of you guys that are in class, we still have 30 minutes. So you should be able to actually finish Delta Math in 30 minutes. If you're still working on Delta Math from other days, do this one first and then go back and work on any late ones that you have, because you can still get credit for those. So I recommend doing that. And those of you guys online are welcome to stay as always, or you may choose to log off. I'm going to walk around and help the group that's here. If you're online and need help, just shout out so that I know you need help, and I will come back.